Hello and welcome to my presentation on Coulomb's law. The first thing we need to discuss is conservation of charge. We've learned that the Benjamin Franklin electric charge model, as well as the model of the atom developed by various scientists throughout the years, consists of physical objects, protons and electrons, which each carry a known specific amount of charge. This is where the charge comes from, and electrons and protons are actual physical objects. They are matter. So in a closed system, charge can't be created and it can't be destroyed. It's really good to have an analogy in your mind, such as a jar of marbles, where the marbles represent electrons, for instance, charged objects. If the jar were open, you can add electrons, you could take them out. But once the lid's closed, whatever electrons started in the jar will be the same amount that remain in the jar. That's the concept of conservation of charge. Charles Coulomb was a physicist and engineer who lived in the 1700s. He did a lot of research and testing with electric charge. He invented a device called a torsion balance that could be used to test forces between charged particles. The torsion balance was a closed system in which Coulomb placed known amounts of charge on metal-coated spheres. These spheres attracted or repelled each other, which twisted a fiber whose torque properties were known. The torsion balance also included a scale measuring distance. In this way, testing various charges on particles and measuring the distance between them, Charles Coulomb was able to calculate the force between the particles and develop a theory and equation of static electric force. So charges or charged objects exert forces called electrostatic forces or Coulomb forces on each other. And Coulomb's law enables us to quantify the forces. Specifically, Coulomb's law deals with spherical small charges called point charges. Due to the small nature of the charges, forces between them is always along the line between the charges. So that's an important property that we need to keep in mind. You can think about this as the force of gravity between two planets, which would be along the line between the planet centers. So the results from Coulomb's testing showed that the force between 2 point charges is proportional to the charge on each of the charges. Or in other words, the force between them is proportional to the absolute value of the product of the two charges. Also, the force is inversely proportional to the square of the distance between the charges. Based on all the data collected from these tests, Coulomb was able to determine a constant that made the proportionality into a final equation. This constant, called the Coulomb's constant, denoted by lowercase k, has a value of 8.988 times 10 to the 9 Newton meters squared per Coulomb squared. So how do we use Coulomb's law? Well, first of all, we're dealing with forces. So all of the introductory mechanics equations apply. Newton's 3 laws apply, conservation of energy, and linear momentum. Depending on the problem that we're dealing with, we may use any of these. Typically, Coulomb's law problems involve particles called point charges, as I mentioned, and the point charges are usually held fixed by some unknown external force. The reason we do this is so that we don't need to calculate accelerations, and that greatly simplifies problems. Since particles can be oriented on 2 or even 3 axes, we need to understand and employ vector math to solve many of these problems. So it's important to brush up on trigonometry and vector math and to know how to find magnitude and angle of a vector given the I, j, and k components along each axis, and vice versa. Also, it's important to know how to project vectors along different axes using cosines. The simplest type of Coulomb's law problem would be one involving only 2-point charges, in which case the forces would be along a single axis, and the vector math is greatly simplified because we're only dealing with positive and negative direction along the single axis. So here's a simple one-dimensional problem. We've got a 5 microcoulomb and a negative 3 microcoulomb point charge that are 9 nanometers apart as shown. It's probably a good idea to brush up on your prefixes for this. So here we're trying to solve for the force exerted on the 5 microcoulomb charge due to the negative 3 microcoulomb charge. Now I'm going to walk you through step by step solving a problem like this. Step 1 is to define an axis system. So in the top right hand corner I'm showing the XY axis that I've chosen. In this case, the forces are going to lie solely along the x-axis, and they can be positive or negative. Step 2 is to label the charges as variables. For Coulomb's law problems, typically we use the variable capital Q or lowercase q to denote charge. So here we have Q1 and Q2 as shown. Step 3 is to define the separation distance as a variable. Typically we use the variable lowercase r as shown. Step 4, we need to recall what the value of the Coulomb constant is. And so I'm showing that here, lowercase k. Step 5, now we apply Coulomb's law to solve for the magnitude of the force. So since we're solving for the magnitude of the force that the negative 3 microcoulomb charge exerts on the 5 microcoulomb charge, we're solving for the force that Q2 exerts on Q1, and we call that force F2 on 1 as shown. When we plug all of the numbers in, we're able to solve for F2 on 1, which equals 1.7 times 10 to the 15th newtons. So now we have the magnitude, we draw the vector direction. And the way that we draw vector directions for Coulomb's problems is based on laws of attraction and repulsion for the charges at hand. So here we see that we have opposite charges, so they're going to attract, and then we can see that the force acting on Q1 will be toward the right. So now we have the I hat vector, positive I hat in this case. So our final answer ends up being F2 on 1 as a vector is equal to 1.7 times 10 to the 15th newtons I hat. And the problem solved. Now that you've seen how to solve a simple Coulomb's law problem, let's take a look at a slightly more difficult problem, which is a two-dimensional problem. In this problem, we have two positive point charges, Q2 and Q3 as shown, and we have one negative point charge, Q1, and the values are shown. And we see the orientation of these 3-point charges, which I set up as a 3, 4, 5 right triangle to make things easy. And what we're trying to solve for in this case is the net force acting on particle 1 due to the other two particles. So we want the force on Q1 due to Q2 and Q3 interactions. In other words, we want a final vector, magnitude, and angle that shows the combined effect of the force between Q2 and Q1 and Q3 and Q1. Now I'll walk you through step by step on how to solve a problem like this. Step 1 is to define an axis system. In this case, I'll use the same axis system that we used before, and in many cases you'll do the same thing. Next, we can draw the force vectors, at least directionally, so we get an idea of what our final vectors will look like. In this way, we will be able to see how to apply Coulomb's law and what distances we're looking at. Keep in mind here that the reason for the direction of the vectors is because of the attractive or repulsive force. So here we see that Q2 and Q3 attract Q1. Step 3, we define the distance between the charges. As we can see, the distance between Q1 and Q2 is 4 millimeters, and the distance between Q1 and Q3 is 5 millimeters. So those are our R values. Step 4, we write the Coulomb's law equations for each force. Here we see that we've plugged in numbers for F2 on 1 and for F3 on 1. And if you go through the math, you should find that these values are 3.6 times 10 to the 10th newtons and 1.2 times 10 to the 10th newtons. So that's our vector magnitudes. Step 5, now we write each force vector in terms of its I and j components. So in order to do that, we need the angles, theta 1 and theta 2, as shown, in order to project the vectors along the x and the y axis to get our I component and our j component, respectively. So since this is a 3, 4, 5 right triangle, we can Google that and find out that the angles are 36.87 degrees and 53.13 degrees. So F2 on 1 is really easy to solve because it only points along the negative x-axis. So we're going to get a negative I component for that vector. And so that value is shown here. F3 on 1 is a little more tricky, but we see that if we take the cosine of theta 1, we'll get the x component. So we project along the x-axis. And that'll also be negative as shown. And if we take the sine, then we'll get the y component, which is, again, negative. So take note of why it's very important to draw the vectors in the beginning, because that way you can see whether the components are going to be positive or negative and along which axis. And then you can get an idea of which component will be larger, so that if you get incorrect answers in your math, you'll recognize it right away. Here we can see that the x component of F3 on 1 will be larger than the y component due to the fact that the angle is less than 45 degrees. So plugging in values and simplifying, we get F3 on 1 in terms of its I and its j components. Now the next step is to add vector components of F2 on 1 to the vector components of F3 on 1 to get the net force acting on particle 1. To do this, we add the I components together, and that's one number. Then we add the j components together, and that's our other number. And then we rewrite F net on 1 in terms of a single I and a single j component, as shown. Here we get negative 4.6 times 10 to the 10th newtons in the I direction, and negative 7.2 times 10 to the 9th newtons in the j direction. Now let's visualize the net force vector. We can do that by simply using a graph, and we don't need to use the 10 to the 10th factor here. All we need to know is that the x component is 10 times greater and that it is a 4.6 versus a 7.2. So we want to calculate the slope of the vector, and in order to do that, it's negative 7.2 divided by negative 46, which equals 0.157. So here I'm showing the vector, which is 4.6 long in the x direction and 0.72 long in the y direction. So now we solve for the magnitude and angle. Keep in mind, depending on the problem, you might be asked to solve for the angle with respect to the vertical axis or to the horizontal axis. In this case, we're going to solve the angle with respect to the horizontal axis, which is more typical. So here I call that angle phi, and phi is equal to the inverse tangent of 7.2 times 10 to the 9th divided by 4.6 times 10 to the 10th. Notice here that we use absolute values for these magnitudes. We do this because we've already defined the direction for the vector, so we want to get the acute angle, the angle less than 90 degrees for all of these, and that'll be consistent. We know what the vector looks like based on laws of attraction and repulsion, keep in mind. So when we calculate the angle, we see that it's 9 degrees approximately. And now in order to find the magnitude of the vector, we use the Pythagorean theorem, and we take the square root of the squares of each component magnitude. So doing that gives the final net vector magnitude, and the problem's done. Keep in mind that determining magnitude and angle vectors from the components and vice versa is an introductory mechanics technique, so this is kind of a review for us. Hopefully now you understand how to apply Coulomb's law to both one-dimensional and two-dimensional problems. And if you have any questions, don't hesitate to email me.